All right, so this is part 2 for the AP Calculus BC 2019 MCQ. So number 10, the second derivative of a function f is given by f double prime of x is equal to x times x minus 3 to the fifth power times x minus 10 squared, at which the following values of x as the graph of f have a point of inflection. Now, to get the potential candidates for the points of inflection, let's set the second derivative function that we're given equal to 0. And so the first 0 would be x is equal to 0. The second 0 would be x is equal to 3. And the third 0 would be x is equal to 10. Now, these are just candidates at this point for the points of inflection. To check if these are going to be points of inflection, let's perform a second derivative test. So let's make a number line. And we'll plot all these numbers on the number line. We have 0, and we have a 3, and we have a 10. All right, so now to check if these values of x would be points of inflections, you want to check to see what the symbol is for the second derivative, and let's perform a signs analysis to see if the second derivative goes from positive to negative or from negative to positive at these x values. So let me plug in some numbers on all these bounds. Let's plug in -1 for the left-hand bound before 0, and then between 0 and 3 we can plug in 1. Choose convenient numbers that are going to be easy to plug in. Then between 3 and 10 we can plug in 4. And above 10, let's plug in 11 for that. All right, so I'm going to plug these numbers in for the second derivative to see what the concavity is, whether it's positive or negative. So let's plug in an x value of -1, and then the x value of 1, and then the x value of 4, and then the x value of 11. Now, if you plug in -1 for every x in the second derivative function, then the first factor is x, which we don't care about the value of the second derivative when x is -1. We just care about the symbol. So if you plug in -1 for every x, then the first number is -1. The second value, we have -1 minus 3, which is a negative number, -4. -4 to the fifth power, since the power is odd, and we have a negative value within the parentheses, it's going to be some negative number. So I'll put negative. And then the last factor is being squared, x minus 10 squared. So that's always going to be a positive number. Now, negative times positive would be an overall positive symbol. So at -1, we have a positive symbol for the second derivative. Now, if we plug in 1 for every x, the first factor is going to be positive 1. Second factor is 1 minus 3, which is -2. And the odd power for some negative number would be negative. Okay, and then the last factor is always going to be positive because we're squaring the number. And positive times negative times positive would be an overall negative symbol. Okay, so now let's plug in 4. So the first factor is just going to be x, which is 4, and that's positive. Second factor is 4 minus 3, which is a 1, and 1 to the fifth power is going to be positive. Then if we plug in a 4 for the last factor, we have 4 minus 10, which is -6 squared, which is going to be, again, positive because we have a squared factor. And positive times positive times positive would be an overall positive symbol. Okay, now the last one for 11. So the first factor is 11, which is positive. The second factor would be 11 minus 3, which is 8. And the fifth power of a positive number would be positive at the end. And then 11 minus 10 squared, that's going to be positive. All right, so positive times positive times positive gives us an overall positive symbol. And now at the 11 mark, past 10, we have a positive symbol for the second derivative. Now let's check to see where the symbol changes. We have a sign change from positive to negative at x is equal to 0. So this would be our first point of inflection. Then at the x value of 3, we have a sign change from negative to positive. So the second point of inflection would be at 3. And we don't have any sign change from positive to positive at the 10 mark. So 10 would not be a point of inflection because by definition, a point of inflection would be when the concavity of the original function changes. And at the x is equal to 10 mark, it doesn't change any concavity. It's still concave up before 10 and after 10. So there's only 2 points of inflection, which is 0 and 3, and that would be choice B. All right. Now, number 11, let's evaluate the integral from 0 to pi for e to the x minus 1 over e to the x minus x dx. Now, just by looking at this, we know right away that this would be a u-substitution problem. Because if we choose u to be the denominator, then the derivative of u is in the numerator, which is going to be very convenient for us. So let's use u-substitution, where the u would be e to the x minus x. Again, the rules for choosing u and u-substitution would be that you would check to see if it's some inner function or if it's some denominator, and check to see if the derivative of the u term is somewhere within the integrand. So, and then du would be the derivative, which is e to the x has a derivative of e to the x, and negative x has a derivative of -1. Then let's put the dx symbol. All right, so now this is very convenient for us because e to the x minus 1 dx, well, that's right over here. This entire term will get replaced with du. And now let's change our bounds as well. So the x value, the lower bound of the x value of 0, let's get the u value for that. So u would be e to the 0 minus 0, and that gives us a, e to the 0 power would be a 1, and 1 minus 0 gives us a 1. So the x bound of 0 becomes a u bound of 1. Now the x bound of pi, the upper bound, let's plug that in as well. So u would be e to the pi minus pi, which cannot be further simplified. Okay, so now that we're ready for the substitutions, let's make all the subs. So we then end up getting the integral from, we no longer have 0 and pi. The lower bound of 0 became a 1, and the upper bound of pi became e to the pi minus pi. And now the entire term of e to the x minus 1, we will plug in a du for that. And then for the denominator of e to the x minus x, we said that was our u. So we have 1 over u. And now that we have everything in terms of u's, the bounds and the integrand, we can now perform the integration. The integral of 1 over u would be ln of the absolute value of u. Then we have a plus c. Oh, sorry, there's no plus c for this because it's a definite. Let me get rid of that. So let's evaluate this from the bounds of 1 through e to the pi minus pi. All right, so if we plug in the upper bound, we have ln of e to the pi minus pi. And then let's take away the lower bound, which we have ln of 1. Now, we know what ln of 1 would be. That would be a 0, right? Because ln of 1 is pretty much asking that e to what power gives us a 1, and that would be a 0. So this entire value is gone, 0, and the answer would be ln of e to the pi minus pi. And that would be answer choice D. Alright, so number 12, the table above gives selected values for the differentiable function f. In which of the following intervals must there be a number c such that f prime at c is equal to 2? Now, since we're given that the derivative at c is equal to 2, we're looking for some x interval where the slope between the two x bounds would be equal to 2. So let's plug everything into f of b minus f of a over b minus a. And now whichever one gives us a value of 2 would be the answer. So if we test out a, we have f of b would be f of 4 minus f of 0 over 4 minus 0. Now f of 4 would be a 0, minus we have f of 0, which is an 8, over 4 minus 0 would be a 4, and that gives us a negative 8 divided by 4, which would be a negative 2. So that would not be the answer because between the x bounds of 0 and 4, we will have a number c such that f prime at c would be negative 2, but we're looking for the slope to be a positive 2. Now b, we have f of 8 minus f of 4 over 8 minus 4. And now f of 8 would be a 2 minus f of 4, which is a 0, over 8 minus 4, which is a 4. And that gives us a 2 over 4, which would be a 1/2. So that would also not be the answer. All right, now see, we have f of 12 minus f of 8 over 12 minus 8. And f of 12 would be a 10 minus f of 8, which is a 2, over 12 minus 8 would be a 4. So 10 minus 2 is an 8, and 8 divided by 4 does give us back a 2. So that would be the answer. And let's just test out D. We have f of 16 minus f of 12 over 16 minus 12. And now f of 16 would be a 1. F of 12 would be a 10 over 16 minus 12 would be a 4. And that gives us a negative 9 over 4, which would not be the answer. So number 12 would be C. All right, so now number 13. Let y equals to f of x be the solution to the differential equation dy dx is equal to x plus 2y with the initial condition that f of 0 is a 2. What is the approximation for f of negative 0.4 obtained by using Euler's method with two steps of equal length starting at x is equal to 0? Now, we have two steps of equal length, so let's get our delta x for this Euler's method. We know that the initial value of x is a 0, and we're stopping at negative 0.4. So to get the delta x, we have delta x would be equal to b minus a over n. And where a would be a 0 and b would be a negative 0.4. So if you plug it all in, then delta x would be negative 0.4 minus 0 divided by n, which we have two subintervals, so divided by 2. And now that's going to be negative 0.4 divided by 2, which is a negative 0.2. All right, so if we set this up, let's make our table, x and y. And the initial condition is f of 0 is a 2, so when x is a 0, then y would be a 2. And now we're counting by a delta x of negative 0.2. So 0 minus 0.2 gives us a negative 0.2. And then negative 0.2 minus 0.2 again gives us a negative 0.4. Okay, now that we have all the x's, let's move on to getting the y values. And this right here would be the answer. So to get the next y value that comes after 2, let's take the first y value of 2, this 2 over here. Then let's add to that our delta x, which is a negative 0.2. And then multiply that by plugging in this 0.02 in place of the derivative function, which is x plus 2y. So the x is a 0. Then plus we have twice y, which is twice 2. And let's figure out what that number would be. That's 2, and then again, positive times negative would be an overall negative symbol. And then we have 0.2 times 0.2. And then times 0 plus twice 2 is a 4, so that's going to be a 4. Okay, and now that gives us a 2 minus, let's check what 0.2 times 4 would be. That would be a 0.8. So 2 minus 0.8, which gives us a 1.2. All right, so then the next y value would be a 1.2. And now the same process we would do to get the next y value. So take the previous y value of 1.2. Then let's add to that the delta x, which is a negative 0.2. Then you plug in the previous point, the point that we're on, in place of x and y for the derivative, which is x plus 2y. So x is a negative 0.2. Then plus we have twice y, which is twice 1.2. All right, so there's a bunch of decimals, but shouldn't be that bad. We then have a 1.2, and then positive and negative is an overall negative 0.2. And then times we have negative 0.2 plus twice 1.2 gives us a 2.4. All right, so that's 1.2. And then minus 0.2 times negative 0.2 plus 2.4 would be a 2.2. All right, so, and then from there we have 1.2, and then minus 0.2 times 2.2 would be a, let's see, let's do the work on the side. So 2.2 times 0.2 would be, twice 2 would be a 4, that's going to be a 4, 0, 0, 4, 4, 0, yeah, 0.44. And 1.2 minus 0.44, let's do the work on the side for that. So 1.20 minus 0.44, that's a 10 minus 4 would be a 6, that's a 11 minus 4 would be a 7, and that would be a, 0. Okay, so that would be a 0.76, And that would be the answer for this. So we approximated what the value was for f of negative 0.4 using two steps with equal length, given the initial condition that f of 0 is equal to 2, and given what the derivative function is. And that would be choice A. All right, so now number 14, what is the slope of the line tangent to the curve, the square root of x plus the square root of y is equal to 2 at the point 9/4, comma 1/4? So now this would be implicit differentiation. To get the slope of the tangent line, you want to get the derivative, then plug in for every x and y, whatever the point is that we're plugging in. So let's set this up. We have the square root of x plus the square root of y is equal to 2. And now let's get the derivative for the entire implicitly written function. So the derivative of the square root of x with respect to x would be 1 over twice radical x using the power rule. And then the derivative of the square root of y. Now keep in mind that we're deriving with respect to x, and this has a y variable. So we get the general derivative, but then using the chain rule, so we have 1 over twice radical y. Using the chain rule, y would be a function of x's, so we have to write down the dy dx. Every time we have any implicitly derived function, you want to multiply it by the inner function's derivative, which is y. And that is equal to the derivative of 2, which would be 0. All right, so now let's solve for dy dx. We have, or rather, we can plug in the given point 9/4 and 1/4 for every x and y, and then solve for dy dx. So 1 over twice radical x is a 9/4, so 9 over 4. Plus we have 1 over twice radical y, which is a 1/4. And then times dy dx is equivalent to 0. All right, so if we simplify that, we have 1 over twice, the square root of 9 would be a 3, and the square root of 4 would be a 2. Then plus we have 1 over twice, the square root of 1/4 would be a 1/2. All right, let's bring it up here. So now these twos cross out, and we have 1/3. And these twos also cross out. So 1 over 1 is just 1. And 1 times dy dx would be simply just dy dx. And that is equivalent to 0. All right, now to solve for the derivative, which is our slope, we take away 1/3 on both of our sides. And dy dx, the derivative at that point would be simply just a negative 1/3. And that would be the answer for this, which is choice B. All right, so number 15. Let's get the integral from 1 through infinity for 6 over x plus 3 to the 3/2 power. Now this is an improper integral, so let me compute the integral on the side first, and then I'll plug it back in. So let's bring this. Let's get the indefinite integral, and then we'll get the bounded integral. So the integral of 6 over x plus 3 to the power of 3/2 with respect to x. Let's set this up for us to use u-substitution. So should be the integral of 6, which can be pulled out, but I'll leave it here, I guess. Then times x plus 3 to the power of negative 3/2. All right, so to properly set this up, we put this in such a way that we can eventually use the power rule for integration. And so let's use u sub, where u would be equal to the inner function of x plus 3, and then du would be dx. All right, and that gives us the integral of 6 times u to the power of negative 3/2, and dx becomes du. Okay, so now that we have everything in terms of u's, let's integrate. So we add 1 to our the power of u, which negative 3/2 plus 1 gives us a negative 1/2. So 6u to the power of 1/2, and then negative 1/2, then divided by negative 1/2. And that would be, and then plus c, of course, and then that would be equal to 6 divided by 1/2 would be 6 times negative 2. So negative 6 times negative 2 would be a negative 12. And then we have u to the power of negative 1/2, and then plus c, which let's plug the u back in for what u really was. So this would become negative 12 over the square root of u, which is x plus 3, and then we have a plus c. All right, so that would be the indefinite integral. Let's and we don't need the c because we have balance for the integral that we're finding. So let's put this in place of the integrand that we have. So we're evaluating this function, negative 12 over the square root of x plus 3, from the bounds of 1 through infinity. And since this is improper, we're going to get the limit as b approaches infinity of negative 12 over the square root of x plus 3 from the bounds of 1 through b. All right, so now just by using substitution, we then have the limit as b approaches infinity of negative 12 over the square root of b plus 3. And then minus, if we plug in a 1, that's a negative 12 over the square root of 1 plus 3. All right, so now we know right away that if b approaches infinity, then the first part of the limit, this would approach 0, since the bottom gets bigger and bigger and bigger. So that would approach 0. And we're left with a negative of negative 12, which is a positive 12, over the square root of 1 plus 3, which is a 4. And that gives us a 12 divided by 2, which would be a 6. All right, so the answer for this would be C, which is 6. All right, so number 16, if dy dx is equal to 2 minus y, and if y is equal to 1 when x is equal to 1, then solve for the y function. So we're solving this differential equation, dy dx is equal to 2 minus y. So to solve it for the original function of y, let's bring all the x's over to one side and the y's over to the opposite side. So if we multiply by dx on both of our sides, that gives us a dy is equal to 2 minus y dx. All right, then if we divide by 2 minus y, that gives us a 1 over 2 minus y dy is equal to 1 dx. Okay, so to undo the derivative, if we integrate both of our sides, then let's perform the integral of 1 over 2 minus y dy on the side. We have the integral of 1 over 2 minus y dy. And let's use u sub for this. So u would be equal to 2 minus y, the denominator. And then du would be a negative dy. All right, and to get the dy by itself, let's divide by negative 1. So dy would be simply just a negative du. All right, so to make the substitution, the dy becomes a negative du, which I'll put the negative on the outer side. Negative 1 du takes the place of dy. And then 1 over 2 minus y just becomes a 1 over u. And that would be a negative of the ln of u. And then we have a plus c. Which if we plug it back in, then that's going to be a negative ln of u is 2 minus y. And then we have a plus c. All right, so keep in mind that whenever we solve differential equations, we never put the plus c on the dependent variable side. So this entire thing just becomes negative ln of the absolute value of 2 minus y. We don't put the plus c on the dependent variable side. Then the integral of 1 with respect to x would be a 1x plus c. Okay, now to solve for the y function, let's first divide by negative 1. We have ln of 2 minus y would be equal to x divided by negative 1 would be a negative x. And then some constant divided by negative 1 would remain a constant, so that's just still plus c. Now, if we get the y by itself, it's e to the power of negative x plus c would be equal to 2 minus y. Okay, now using properties of exponents, let's break up this e power, so that becomes e to the power of negative x times e to the power of c would be equal to 2 minus y. Okay, now we know that e to some constant value would still be a constant, so we can plug in c for that. And that c can be pulled up at the very front of this expression, and that becomes ce to the power of negative x is equal to 2 minus y. All right, now If we subtract away 2 on both of our sides, we have ce to the negative x power minus 2 would be equal to negative y. Then to get the y by itself, we would divide by negative 1, and that gives us a y function of 2 minus ce to the power of negative x. All right, so at this point, we can plug in our point that we were given of 1 comma 1. And now if we plug that in, then we have 2 minus ce to the power of x is negative 1, so negative 1 is equal to y, which is again a 1. And that becomes a 2 minus c over e, because we have a negative first power, is equal to 1. And then if we subtract away 2 on both of our sides, that gives us, let's put it right here, that gives us a negative of c over e would be equal to 1 minus 2, which is a negative 1. Now, since they're both negative, let's divide by negative 1 to make them positive. And then if we multiply by e on both of our sides, then c would be simply just 1 times e, which would be e. Okay, so now that we know what the e value, the c value is, we can plug it back into our solved function. And the answer would be y is equal to 2 minus c, which is an e, and then times e to the power of negative x. And now if we use properties of exponents once again, then we can combine these powers of e using addition, and that gives us a y function of 2 minus e to the power of 1 plus negative x, which would be a 1 minus x. All right, and that corresponds to, let's see what choice it should be. 2 minus e to negative x corresponds to choice e. And that would be the answer for this. Oh wait, sorry, that's not C. It corresponds to B. So let me erase that. All right, so 2 minus e to the 1 minus x, which corresponds to choice B. All right, so number 17. Which of the following series converges? Now, all of these are alternating series because we have a term of negative 1 to the power of n. So by the alternating series test, we must check if the limit as n approaches infinity is equal to 0. The limit as n approaches infinity if of a sub n is equal to 0. If this condition is satisfied, along with the condition that the functions, the series is decreasing for every value of n in the bounds given, then it's going to be a convergent series. So if we test a out, the limit as n approaches infinity for 1 minus n over n. And now the limit to infinity for any given function would be the horizontal asymptote of that function. And since we have the same power of n at the top and the bottom, it should be the whole number ratio of their coefficients, which is negative 1 over 1. And that limit would be a negative 1, which is not equal to 0. So that's not going to be, or like we cannot prove it to be convergent using the alternating series test. So A would not be the answer. Then for B, we have the limit as n approaches infinity for n plus 1 over 2n. Now we can divide by the biggest power of n in the denominator to see what this limit would be. But again, since we have the same power of n at the top and the bottom of 1, it should be the whole number ratio for the limit to infinity, and that would be a 1/2, which is again not equal to 0. So B would also not be the answer. Then for C, we have the limit as n approaches infinity of n squared over 3 times the square root of n. Okay, so now since we don't have the same power at the top and the bottom, we have it's a top heavy function. This function has a slant asymptote, so the limit would not be a 0 for sure for that. Even if we solve for the limit using by dividing every power of n at the top and the bottom by the biggest power of n in the denominator, that would not give us a 0. So C would not be the answer. Then D, let's get the limit as n approaches infinity for twice the square root of n over n. Now, since this function has a bigger power of n at the bottom, since the radical n has a power of 1/2 and the bottom has a power of 1, this limit to infinity would be 0 because we have the horizontal asymptote for any function would be a 0 if it's bottom heavy. So since this condition is satisfied and the given series would be a decreasing series, D would be a convergent series. So that would be the answer for this. All right, so then number 18. Let R be the region in the first and second quadrants between the graphs of the polar curves. F of theta is equal to 3 plus 3 cosine theta, and g of theta is equal to 4 plus 2 cosine of theta, as shaded in the figure above. Which of the following integral expressions gives the area of R? So we're not getting what the area is, we're just getting which expression would give us the area. So now, if we recall, the area for a polar curve would be the integral from, or like what it's 1/2 of the integral from alpha to beta of r squared with respect to theta. All right, so since we're given not one but two polar curves, it should be 1/2 of the integral from alpha to beta of r1 being squared and then minus r2 squared with respect to theta. All right, so now r1, the first polar function would be the 3 plus 3 cos theta, which is graphed right here. So from the origin to there, all that area would be the r1, which is again equal to the 3 plus 3 cos. Let me put that here. 3 plus 3 cosine theta, our cardioid. And then r2 would be the area from the pole to the second curve, which would be 4 plus 2 cos theta. So r2 would be simply just a 4 plus 2 cosine of theta. And now, so we know what r1 is and what r2 is. Now, what about the alpha and the beta? Well, since we're talking in terms of polar coordinate points, everything would be in terms of theta. So at the unit circle, this would be the 0 mark, and that would be the pi mark, and that's where the curves are shown. So this point would be at the 0 mark, and that point would be at the pi mark, and therefore alpha would be 0 and beta would be pi. So if we plug everything in, that I believe corresponds to choice D. We have 1/2 of the integral from 0 to pi, which is alpha and beta, of g of theta, which was the 4 plus 2 cos theta function. That's g of theta squared. So r1 squared, and then minus we have r2 squared, which is the inner function, and that would be f of theta, which was the cardioid of 3 plus 3 cos theta. So D would be the answer for that. All right, and then we have number 19. Which of the following statements about the series from 1 through infinity of -1 to the n times n over n squared plus 1 is true? All right, so now A, the series can be shown to diverge by comparison with 1 over n. Let's read further. So the series can be shown to diverge by limit comparison with 1 over n, or the series can be shown to converge with comparison with 1 over n squared, or D, the series can be shown to converge by the alternating series test. Now, if we didn't have the -1 to the n power, then we might have been able to use comparison to tell if that series itself would be convergent or divergent. But since we're giving an alternating series, we can use the test for this. And so if the accompanying series a sub n, which is n over n squared plus 1, if the limit as n approaches infinity for this would be a 0, which it is, because the limit to infinity again would be the horizontal asymptote, and this is a bottom heavy function. So the limit to infinity would be the x-axis, aka y is equal to 0. Since this condition is satisfied, and the series is decreasing, and every term is positive, this can be shown to be convergent by using the alternating series test, which is D. So 19 would be D. All right, so number 20. If the integral from 1 through 4 of f of x is equal to 8, and the integral from 1 through 4 of g of x is equal to -2, which of the following cannot be determined from the information given? All right, so A, can we get the integral from 4 through 1 for g of x? We can, because we're given what the integral is from 1 through 4 for g of x. It's given to be -2. And now if we ever have improper bounds, then we can flip them over and then take negative of what the value for that should be. So this would be simply just negative of the integral from 1 through 4 of g of x dx. And we know what that value is. This value is given to be a negative 2. So negative 1 times negative 2, which would be a 2. All right, so similarly, we can get the value for b as well. Since the 3 can be pulled out, these are properties of integrals, which we can pull out coefficients for the entire integrand. And 3 times the integral from 1 through 4 of f of x, we can get that because we know what the integral of f of x is from 1 through 4. All right, so b would not be the answer because we can get that value. Then what about c? So can we break up integrals using multiplication? We cannot. We would need integration by parts for that, but we're not given enough information in the problem to get what the value for this is, even if we do use integration by parts. So C would be the answer because we cannot break up integrals using multiplication. D we can do because we can pull the 3 out as a coefficient for the f of x and then add that with the g of x bounds from 1 through 4. So D we can get, but we cannot get C. So C would be the only one that cannot be determined from the information given.